Hey everyone, what's up guys? Okay, let's go. Number 10. Supermassive black holes in the early universe. Let's start with something that genuinely keeps astronomers up at night. Black holes that are way too big, way too early. Now, if you followed space news even a little, you probably know what a black hole is. A region of space where gravity is so intense that nothing, not even light, can escape. We usually talk about them forming when massive stars run out of fuel, collapse under their own weight, and leave behind a dense remnant. That's the standard story. And it works fine for the black holes we see in our cosmic neighborhood. They're a few times to maybe a few dozen times the mass of the sun, totally reasonable. Totally expected. But then we point our telescopes farther out. And farther out in space means farther back in time. Light takes time to travel, so when we look at galaxies billions of light years away, we're seeing them as they were billions of years ago. And what we found out there doesn't make sense. We've detected supermassive black holes, objects with millions or even billions of solar masses, sitting in the centers of galaxies when the universe was less than a billion years old. Some of them have been dated to around 700 to 800 million years after the Big Bang. And that's the problem, because black holes don't just appear fully grown. They have to feed. They have to pull in gas, dust, stars, merge with other black holes, and slowly, over hundreds of millions or billions of years, build up that kind of mass. There's a theoretical speed limit to how fast a black hole can grow, called the Eddington limit. It's basically the point where the radiation pressure from a material falling and pushes back hard enough to slow down further accretion. You can cheat a little maybe with chaotic gas flows or direct collapse scenarios, but even with the most generous models, you simply don't have enough time to grow a 10 billion solar mass black hole in under a billion years. And yet they're there. Quasars like J1342+0928, discovered by the Sloan Digital Sky Survey, host black holes around 800 million solar masses when the universe was only about 690 million years old. More recently, the James Webb Space Telescope has been finding even earlier candidates. Galaxies with active, feeding black holes that shouldn't have had time to form, let alone grow to that scale. It's like finding a fully grown oak tree in a forest that was planted last Tuesday. So what's going on? Are our models of black hole growth wrong? Maybe. Some researchers think the first black holes didn't form from stars at all. Maybe they formed from massive clouds of primordial gas collapsing directly into black holes tens of thousands of times the mass of the sun. That would give them a huge head start. Others suggest that early universe conditions allowed for periods of super Eddington accretion, where black holes essentially gorged themselves far beyond the theoretical limit, maybe because the gas was colder, denser, or flowing in from multiple directions at once. There's also the possibility that we're misunderstanding how early galaxies assembled. Maybe mergers happened faster, more violently, and funneled material into the center much more efficiently than we thought. But here's the thing that really bothers physicists. Even if you stretch every parameter, even if you assume the most favorable conditions, the math still struggles to catch up with the observations. We're not talking about a small discrepancy. We're talking about objects that appear to break the timeline of cosmic evolution. And when reality outpaces your equations, that's usually a sign that something fundamental is missing from the picture. Maybe the first stars were far more massive than we thought, living fast, dying young, and leaving behind heavier seeds. Maybe dark matter played a role in funneling gas faster. Maybe there's a whole population of intermediate black holes we haven't detected yet that merged rapidly in the early universe. Or maybe, and this is the uncomfortable part, our understanding of how gravity, radiation, and gas interact in extreme environments is incomplete. What makes this even more fascinating is that these early supermassive black holes aren't just sitting there. They're actively shaping their host galaxies. The energy they release as they feed can blow gas out of the galaxy, shut down star formation, and regulate how the entire system evolves. So if they formed too early, that means galaxy evolution itself might have started on a completely different schedule than our models predict. We're still gathering data. JWST is peering deeper into the infrared, catching light from galaxies that formed in the cosmic dawn. New radio arrays are mapping the environments around these ancient quasars. And every new discovery seems to push the timeline further back, forcing theorists to rewrite their simulations. It's a beautiful, frustrating, completely normal part of science. But make no mistake, these early supermassive black holes are a direct challenge to the standard picture. They shouldn't be there. Not yet. Not that big. And the fact that they are means we're missing a piece of the puzzle. Maybe a big one. Number 9, the Great Attractor. Now, let's talk about something that sounds like it was pulled straight out of a sci-fi novel, but is very real, very massive, and very poorly understood. The Great Attractor. If you've ever looked up at the night sky, you probably imagine the Milky Way just sitting there, peacefully rotating, minding its own business. But that's not really what's happening. Our galaxy, along with thousands of others in our local region of space, is moving. And not just drifting. We're being pulled. At roughly 600 kilometers per second. That's over 2 million kilometers per hour. toward a specific point in the sky. And for decades, we had no idea what was doing the pulling. The discovery came in the 1970s and 80s when astronomers started mapping the motions of galaxies relative to the cosmic microwave background. They noticed a coherent flow. Galaxies weren't just expanding away from each other due to the universe's overall expansion. They were also sliding in a particular direction, like water draining toward a sink. When they traced the vectors back, they all pointed to a region in the sky near the constellations Norma and Centaurus. But when they tried to look there, they hit a wall. Literally. That region sits directly behind the dense disk of our own Milky Way. Astronomers call it the zone of avoidance because the dust, gas, and stars in our galaxy's plane block visible light from whatever lies beyond. It's like trying to see what's on the other side of a fogged-up window while standing in a crowded room. You know something's there, but you can't get a clear look. So they switch to other wavelengths. Radio, infrared, X-rays, and slowly a picture emerged. There's a massive concentration of galaxies out there. The Norma cluster, part of a larger structure called the Laniakea supercluster, which actually includes our own Milky Way. The mass required to generate that kind of gravitational pull is staggering. We're talking about tens of thousands of galaxies, plus all the dark matter holding them together, creating a gravitational well so deep it's dragging entire galaxy clusters toward it. But here's where it gets weird. Even after mapping what we can, the numbers don't quite add up. The visible mass in that direction doesn't fully explain the velocity we're measuring. There's still a missing component. Either there's more mass hidden behind the galactic plane than we've detected, or the gravitational influence is coming from something even larger, something beyond the Great Attractor itself. And that's exactly what later surveys suggested. The pull isn't just coming from one spot. It's part of a much larger cosmic flow. Beyond the Great Attractor lies the Shapley supercluster, one of the most massive known structures in the nearby universe. And beyond that, there are hints of even larger concentrations of matter. Some researchers talk about the dipole repeller, a vast, nearly empty region of space on the opposite side of the sky that's essentially pushing us away by lacking gravitational pull. So it's not just one thing dragging us. It's a combination of being pulled toward dense regions and pushed away from empty ones. Gravity doesn't just attract. The absence of it creates motion too. But even with all that, the Great Attractor remains deeply unsettling, because it reminds us how limited our perspective really is. We're embedded inside a galaxy, looking out through a dusty disk, trying to map structures that span hundreds of millions of light years. And the thing that's literally moving our entire cosmic neighborhood is partially hidden from us. We infer it from motion. We model it from redshift surveys. We piece it together from radio telescopes and infrared maps. But we've never seen it clearly. Not in the way we've seen other superclusters. And there's another layer to this. The scale of these structures pushes against what cosmology says should be possible. The universe is supposed to be homogeneous on large scales, meaning if you zoom out far enough, matter should be evenly distributed. But superclusters, cosmic voids, and gravitational anomalies like the Great Attractor suggest that matter is clumped in ways that challenge that assumption. Some simulations struggle to reproduce structures this massive this early. Others suggest we're just seeing the natural result of dark matter scaffolding pulling baryonic matter into filaments and nodes over billions of years. But the motion itself is real. We are falling toward it. The local group, the Virgo cluster, thousands of galaxies, all streaming in the same direction. And we won't ever reach it. The expansion of the universe will outpace the pull long before we get close. But the fact that it exists, that it's massive enough to override local expansion, and that it's partially hidden from direct observation, it's a humbling reminder of how much of the cosmos we're still guessing at. Physics says gravity should be predictable. Mass here, motion there. But when the mass is hidden, the motion is coherent across millions of light years, and the structure defies easy classification, you start to realize that predictable is a relative term. The Great Attractor isn't breaking physics. It's just operating on a scale that makes our model sweat. And that's exactly why it belongs on this list. Number 8, dark energy and the accelerating universe. Alright, let's talk about the single most embarrassing discovery in modern cosmology. Dark energy. I say embarrassing not because it's wrong, but because it completely blindsided us. We had a story. A clean, elegant, mathematically satisfying story about how the universe should behave. And then reality looked at that story and said, nah. Here's the setup. After the Big Bang, the universe began expanding. Space itself stretched, carrying galaxies apart. That part we knew. Edwin Hubble figured that out in the 1920s. But the big question was always, what happens next? Gravity pulls things together. All the matter in the universe, stars, gas, dark matter, should be exerting a mutual gravitational pull. That pull should act as a brake on the expansion. Over time, the rate of expansion should slow down. Maybe it would slow enough to eventually reverse, leading to a big crunch. Maybe it would just coast forever, gradually losing speed. But it should definitely decelerate. That's what general relativity predicts. That's what every simulation showed. That's what every textbook taught. So in the 1990s, two independent teams of astronomers set out to measure that deceleration. They used type I supernovae as standard candles. These are exploding white dwarf stars that always reach roughly the same peak brightness, which makes them perfect for measuring cosmic distances. You observe how bright they appear, compare it to how bright they should be, and you get distance. You measure their redshift, and you get how fast they're moving away. Do this for dozens of supernovae at different distances, and you can trace how the expansion rate has changed over billions of years. They expected to see the curve bending downward, slowing expansion. Instead, they saw the opposite. Distant supernovae were fainter than they should be, meaning they were farther away than a decelerating universe would allow. The only explanation: the expansion isn't slowing down. It's speeding up. The universe is accelerating. When the results were announced in 1998, the reaction wasn't excitement. It was disbelief. People checked the data, checked the calibration, checked for dust, for evolutionary effects, for systematic errors. Nothing explained it away. The acceleration was real, and it meant something was pushing space apart, something with negative pressure, something that doesn't clump like matter, doesn't interact with light, doesn't show up in particle detectors, something that makes up about 68% of the total energy density of the universe. We called it dark energy. And here's the brutal truth: we still don't know what it is. The leading explanation is the cosmological constant, a term Einstein originally added to his equations to keep the universe static, then famously called his biggest blunder when expansion was discovered. But it turns out that constant might actually be real. It represents the energy density of empty space itself. Vacuum energy. Quantum field theory says that even in a perfect vacuum, virtual particles pop in and out of existence, creating a baseline energy. If that energy has the right properties, it could drive accelerated expansion. But there's a problem, a massive one. When physicists try to calculate the expected value of vacuum energy using quantum mechanics, the number they get is about 10 to the power of 120 times larger than what we observe. That's not a small error. That's the worst prediction in the history of science. It's like guessing the weight of a grain of sand and being off by the mass of the observable universe. So either our understanding of quantum vacuum energy is completely wrong, or dark energy isn't vacuum energy at all. Other theories exist. Maybe dark energy is a dynamic field, something called quintessence, that changes over time. Maybe it's a modification of general relativity on cosmic scales. Maybe gravity behaves differently when you stretch it across billions of light years. Maybe we're misinterpreting the data because we're assuming the universe is perfectly homogeneous when it's actually lumpy, and those inhomogeneities are creating an illusion of acceleration. But so far, nothing has replaced the cosmological constant model. It fits the data. It matches the cosmic microwave background. It aligns with large-scale structure surveys. It's just deeply unsatisfying, because it means most of the universe is made of something we can't detect, can't explain, and can't reproduce in a lab. We only know it's there because space is stretching faster than it should, and the implications are wild. If dark energy keeps pushing, galaxies will eventually move beyond our observable horizon. The night sky will go dark. Star formation will cease. Black holes will evaporate. The universe will end in a cold, empty, expanding void. The big freeze. And it's all driven by a force we don't understand. Physics says gravity should win. Matter should pull space back together. But dark energy says otherwise. And right now, dark energy is winning. We're living in a universe that's tearing itself apart, slowly, silently, and we're just along for the ride. That's not just unexpected. It's a fundamental rewrite of how we thought cosmic evolution works. And until we figure out what dark energy actually is, it remains the biggest, should not exist, on this list. Not because it breaks math, but because it breaks our intuition about how reality should behave. Number 7. Stars older than the universe. This one sounds like a joke, or a typo, or a clickbait headline, but it's real. Or at least, it was real enough to cause a genuine crisis in cosmology. Stars older than the universe. Let me back up. The age of the universe is one of the most carefully measured numbers in all of science. We get it from the cosmic microwave background, from expansion rate, from the oldest star clusters, from nucleocosmochronology, which is basically radioactive dating for stars. All the methods converge around 13.8 billion years. Give or take a few tens of millions. That's solid. That's backed by decades of cross-check data. So imagine the surprise when astronomers started measuring the ages of certain nearby stars and got numbers that didn't just approach 13.8 billion, they exceeded it. The most famous case is HD 140283, nicknamed the Methuselah star. It's a metal-poor subgiant about 190 light-years away. Metal-poor means it formed early, before generations of supernovae had time to seed the galaxy with heavier elements. That already suggests great age. But when researchers ran stellar evolution models on it, factoring in its temperature, luminosity, composition, and distance, the initial age estimates came back around 14.5 billion years. Sometimes higher, depending on the model. Now, you don't need a PhD to see the problem. A star cannot be older than the universe it lives in. That's not a physics violation. That's a logic violation. It's like finding a photograph of your grandfather as a child, dated 10 years before your grandparents were born. So what happened? Did we break time? Did the star form in a previous universe? Did our cosmology collapse? No. What happened was a collision between measurement uncertainty and model sensitivity. Stellar age isn't something you can read off a dial. You infer it. You take observable properties, plug them into complex equations that simulate how stars burn fuel, change structure, and evolve over time, and you get an age range. But those models are incredibly sensitive to input parameters, especially distance, especially composition, especially how you treat convection, diffusion, and helium abundance. When the Methuselah star's age made headlines, astronomers went back to work. They refined the distance using Hubble parallax measurements. They updated the oxygen and iron ratios. They adjusted how the models handle element settling in the star's interior. And the age came down, closer to 13.5, maybe 13.7 billion years. Suddenly, it fit within the margin of error. The crisis eased. But here's why this still matters. The fact that we even got close to breaking the timeline reveals how fragile our age-dating methods really are. A shift of a few percent in distance. A slight misestimate of metallicity. A different assumption about how heat moves through a star's outer layers. Any of those can swing the age by hundreds of millions of years. And when you're working near the edge of cosmic time, hundreds of millions of years is the difference between plausible and impossible. More importantly, this tension forced astronomers to confront a deeper issue. Our stellar models and our cosmological models are built independently. One comes from nuclear physics and hydrodynamics. The other comes from general relativity and observational cosmology. They should agree. But when they don't, it's not always clear which side needs fixing. Maybe the star isn't too old. Maybe the universe is slightly younger than we think. Maybe the Hubble constant tension, the disagreement between early universe and late universe expansion measurements, is subtly throwing off our age calculations. Maybe dark energy's behavior in the first few billion years was different than we assume, changing the timeline of structure formation. And it's not just Methuselah. Other ancient stars in the galactic halo, in globular clusters like M92 and NGC 6397, have pushed against the 13.8 billion year boundary. Each time, refinements bring them back into alignment. But the pattern is clear. We are operating at the edge of precision. And at that edge, small errors look like paradoxes. What's fascinating is how this impossible result actually improved science. It forced better parallax measurements. It pushed updates to stellar evolution codes. It highlighted the need for consistent treatment of elemental diffusion. It reminded everyone that age isn't a direct observation. It's a reconstruction. And reconstructions can be wrong. So technically, no star has been proven to be older than the universe. But the fact that we keep finding ones that flirt with that boundary, that keep forcing us to recalibrate, that keep making cosmologists double-check their math, that's the real story. Physics says the timeline should be clean. Reality says measurement is messy. And when messy meets fundamental, you get moments where it looks like the universe broke its own rules. It didn't, but it sure looked like it for a while. And that's enough to earn a spot here. Number 6. Ultramassive neutron stars. Neutron stars are already extreme. They're the collapsed cores of massive stars that went supernova but didn't have quite enough mass to form a black hole. What's left is a sphere about 20 kilometers across, packed with more mass than the sun. The density is insane. A sugar cube-sized piece would weigh about 1 billion tons on Earth. The magnetic fields can be 1 trillion times stronger than anything we can produce in a lab. The rotation can be hundreds of times per second. They're basically cosmic pressure cookers, holding matter in states we can't replicate on Earth. But physics draws a line. There's a theoretical maximum mass for a neutron star. Cross it and gravity wins. The star collapses into a black hole. No warning. No explosion. Just gone. That limit is called the Tolman-Oppenheimer-Fokoff limit. And for decades, we thought it sat somewhere around 2.1 to 2.3 solar masses. Maybe a bit higher if you factor in rapid rotation or exotic equations of state. But the boundary was supposed to be firm. Neutron stars below it. Black holes above it. Clean division. Then we started finding neutron stars that shouldn't be there. PSR J0740 plus 6620. A pulsar clocked at around 2.08 solar masses. PSR J0348 plus 0432. Right around 2.01. Then GW190814, a gravitational wave event that revealed a compact object around 2.6 solar masses. Now that one's debated. It might be the lightest black hole ever found. Or it might be a neutron star that somehow survived past the limit. Either way, it's sitting in the mass gap, a region where theory says nothing should exist. And that's the problem. Because if neutron stars can reach 2.5, maybe 2.6 solar masses without collapsing, then our understanding of how matter behaves at nuclear densities is wrong. Or at least incomplete. Inside a neutron star, atoms don't exist. Electrons are crushed into protons, forming neutrons. But at the core, even neutrons might break down. Quarks might deconfine. You could get strange matter. Hyperons. Pion condensates. Color superconductivity. Theoretical physicists have proposed dozens of exotic states. But we can't test them in a lab. We can only infer them from how massive a neutron star can get before it collapses. So when we find one's pushing the limit, it means the pressure inside is higher than our models predict. Something is propping the star up against gravity. Maybe the strong nuclear force behaves differently at extreme densities. Maybe quark matter provides extra stiffness. Maybe rotation is buying time, though most of these measurements account for that. Or maybe the equation of state, the relationship between pressure and density in neutron star matter, is fundamentally different than we thought. This isn't just academic. The equation of state determines everything. How big neutron stars are, how they merge, what gravitational waves they produce, whether they form black holes immediately or survive as hypermassive remnants for a few milliseconds. It affects our process nucleosynthesis, the creation of heavy elements like gold and platinum in neutron star collisions. It shapes how we interpret signals from LIGO, Virgo, and NICER. And right now, the data is pulling theory in multiple directions. X-ray observations from NICER are measuring neutron star radii with unprecedented precision. Gravitational wave detections are constraining tidal deformability, how much a star stretches before merger. Radio timing is pinning down masses to within a few percent. And all of it is pointing toward a stiffer equation of state than many models predicted, meaning neutron stars can support more mass. Meaning the TOV limit might be higher. Meaning the boundary between neutron star and black hole is fuzzier than we thought. But here's the catch. If you make the equation of state too stiff to support 2.5 solar masses, you run into other problems. You conflict with heavy ion collision data. You struggle to explain certain cooling curves. You create tension with nuclear physics experiments on Earth. So you can't just tweak one parameter. You have to rebuild the model from the ground up. And that's why ultramassive neutron stars are so disruptive. They're not breaking physics. They're stress testing it. They're forcing us to confront the fact that we don't fully understand how matter behaves when squeezed beyond atomic limits. We have equations. We have simulations. We have constraints. But we don't have certainty. And every time a new pulsar measurement drops or a new merger event is detected, the boundary shifts again. Physics says there should be a clean cutoff. Reality says matter is more stubborn than we thought. And until we figure out what's holding these stars up, they'll keep sitting right on the edge of impossibility, reminding us that even the most extreme objects in the universe still have secrets we haven't cracked.